Welcome. Today's video we are talking about section 5.5, which is talking about bases other than e and application problems. So we're going to define exponential and log functions that have bases other than e, differentiate and integrate those functions, and then we're also going to use exponential functions to talk about compound interest and exponential growth and decay. How exciting. Okay, so our first thing we're going to do is we're going to define exponential functions with a base other than a. And since we like e so much, our definition is all about e. So here we have it. A to the x equals e to the power of natural log of a times x. And so if you think about this piece right here, I can rewrite my exponent as the natural log of a to the x. And then e and the natural log are going to cancel, and then I just get my good old friend a to the x. Great. One little stipulation we talk about is that a cannot equal 1, because if a equals 1, then we get a constant function, which is not an exponential function. Boring. So, reminder of our exponent rules. You should know all these rules, but just a little reminder in case you want to write them down. They work for bases other than e as well. All right, let's dig right in with an example. Our first example is radioactive half-life model. So the half-life of carbon-14 is approximately 5,715 years. A sample contains 1 gram of carbon-14. How much will be present in 10,000 years? So a reminder about half-life. So half-life is the number of years required for half of the atoms in a sample of radioactive material to decay. All right, so let's think about this. So let's define some variables here. So we want t to equal time in years. And let's have y equal my amount of carbon-14 in grams. And we got to define where t is, right? So we talk about time, but that doesn't really help. We have to figure out when t equals 1, that's 1 year of what, right? So I want to make sure I talk about t equals 0 being present time. Right? And present time is when I have 1 gram. All right. So let's set up our model. So if I have my amount, and right now I start with 1, and I want to multiply that 1 gram by a half every 5,715 years. So I'm going to take my time and divide it by 5,715. So if I plugged in 5,715, I get 1 times a half. If I plugged in double 5,715, I'm going to get 1 times a fourth, which is a half twice. Okay? So then I want my 10,000 years, so I'm going to plug that in. So y equals 1 over 1 half. And then I have 10,000. You don't have to put that first 1 there, but it's just habit. Okay, so then I do that, and then I plug that bad boy into my calculator. And I'm going to get approximately 3/10 of a gram. And then here's a good old graph to model this. So I see that my initial value is 1 gram. And then after 5,715 years, I get half a gram. And then after that 10,000 years, I get that 3/10 of a gram. Next, some more definitions. Okay, so next definition of logarithmic functions with base a. And once again, we like to change it to base e. So the log base a of x is equal to 1 over the natural log of a times the natural log of x. This is also known as the change of base formula. And it doesn't necessarily have to be e. The definition is base e. But if you wanted to change the base to anything, you can. So change of base formula reminder. So if I have log base a of x, that's equal to log base b of x over log base b of a. So you can change the base from any number to any other number. So reminder of my log properties or rules. So these are the same things we talked about with e, but a reminder that they work with all bases. So we have that the log base a of 1 is 0. We have our log of a product, log of a power, and log of a quotient rules. Okay, next. Properties of inverse functions. So y equals a to the x if and only if x equals log base a of y. So this lets me know that an exponential with base a and a log with base a are inverse functions of each other. So when I compose them together, I am going to get the identity function. So that is 2 and 3. So an exponential with base a and a log base a are going to cancel. And a reminder about my domain. So remember, logs have a domain of all positive numbers. So that will be the domain for 2. But exponentials, my domain is all real numbers. All right. Now let's talk about derivatives. Finally, some calculus. Yes, what you've been waiting for. Let a be a positive real number, not equal to 1, of course, because that's boring. And let u be a differential function of x. So my first derivative is exponential function a to the x, and the derivative of that is the natural log of a times a to the x. And then if I skip down to number 3 here, if I take the derivative of log base a of x, instead of multiplying by that natural log of a, I'm going to divide. So I get 1 over natural log of a times x. And then 2 and 4 here, these are just your good old friend, the chain rule. How exciting. Okay, example 2. Find the derivative of each function. Okay, so our first example is y equals 2 to the x. Maybe I'll keep it like this so we can see the rules. So for example A, if y equals 2 to the x, then just using my little formula here, y prime is going to equal the natural log of 2 times 2 to the x. Then for B, let's see here, B we have y equals 2 to the 3x, so y prime is going to equal the natural log of 2, because that's my base, times 2 to the 3x times the derivative of the exponent, which is 3, so that's chain rule. And when I rewrite that, typically we like to write constants in the front, so I have 3 natural log of 2 times 2 to the 3x. Next example, we have example C. Let's see here, let's do this one over here. So C, we have y equals log base 10, and when it's base 10, that's called common log, and you don't have to write it, so I'm not going to write it. So log of cosine of x. And so then we go ahead and take the derivative of that, and we are going to get 1 over natural log of 10, and then times cosine of x on that denominator as well. And then chain rule, we want to take the derivative of cosine, which is negative sine of x. And then I'm going to go ahead and simplify and say, oh, look, I have sine over cosine. So I get tangent. So then I'm going to rewrite this as negative tangent of x over natural log of 10. Fantastic. And then my last example, I'll do it over here. I got some space. So I have y equals log base 3 of square root of x over x plus 5. I'm going to use my log property to go ahead and make these simpler functions on the inside. So I'm going to rewrite this as log base 3 of square root of x minus log base 3 of x plus 5. Use that power rule to bring out the exponent of a half. Log base 3 of x minus log base 3 of x plus 5. Okay, great. So that we just rewrote y. So now I can take the derivative. So y prime. And I'm going to get... oh my gosh, I need some more space here. All right, so y prime, I'm going to get 1/2, and then log base 3 of x is going to be times 1 over natural log of 3 times x. And then minus, over here, I want the same thing, so 1 over, and then I want the natural log of 3, and then my function inside is x plus 5, and the derivative of that is 1, so I don't have to worry about chain rule there. So then when I rewrite this, I'm going to get 1 over 2x natural log of 3 minus 1 over x plus 5 natural log of 3. And then I'm going to go ahead and combine these because they have a common factor of natural log of 3. So let's just see if we can write it as one fraction. I probably would accept this answer on a test or a quiz, but let's just practice some algebra here. So to find a common denominator, multiply my first fraction by x plus 5, my second fraction by 2x, and then my denominator will be 2x times x plus 5 times natural log of 3. Combine those together, I'm going to get on the numerator 5 minus x, and then 2x times x plus 5 times natural log of 3. Fantastic. Moving on. So we talked about differentiating. Now let's talk about integrating. So our integration rule comes directly from our derivative rules. So if I want to integrate an exponential function with base a, I'm going to get 1 over the natural log of a times a to the x plus c. So instead of multiplying by natural log of a, we're dividing because we're integrated. So find the integral of 2 to the x. So I'm just going to pop that into my little formula here. So I'm going to get 1 over natural log of a, so natural log of 2, times 2 to the x plus c. So I'll just rewrite it as 2 to the x over natural log of 2 plus c. Fantastic. All right, what is next? Applications. Oh, so exciting. All right, so you've done a lot of this before, so compound interest. So here are the two formulas you need to know. So your first one is A equals P times the quantity 1 plus R over N to the power of NT. And so reminder that A is the amount in the account, P is the starting amount or the principal, R is the rate, the annual rate, and N is the number of times it's compounded per year, and T is the number of years. And then if it's compounded continuously, our formula is simplified to A equals P times E to the RT, where E is our good old friend, 2 point whatever. Fantastic. Okay, example 4. A deposit of $2,500 is made into an account that pays an annual rate of 5%. Find the balance in the account at the end of 5 years when the interest is compounded, part A, quarterly, B, monthly, and part C, continuously. Fantastic. All right, so A, quarterly. So for A, I'm going to have my amount. My principal was $2,500, so let's write this down. So this is P, this is R, and this is after 5 years, so that's T, and then these are my N. So N equals 4 here, N equals 12 here, and here I have the continuous formula. So I'm going to use base E. Okay, so part A. So $2,500, and then 1 plus my rate. Make sure you put your rate in decimal form, so 0.05 over compounded 4 times, and then my exponent is going to be that 4 times the 5 years. Plug that into my handy dandy calculator. Oh, I don't need approximate. And make sure you round to the nearest cent. So then I'm going to get 3,205.09. Part B, and we got monthly. So essentially it is the same equation, except instead of 4, I have 12. So let's see how much that is going to increase the amount in my account. So 12 times 5 is my new exponent. I plug that bad boy into my calculator, and I get a little bit more money. I get $3.31 more. So I have $3,208.40. Okay. And then continuously, so I'm going to use the other formula. So A equals PE to the power of RT. Plug in my amounts. So 2,500 times E to the 0.05, and then my 5 years. And for this one, I'm going to get $3,210.06. All right, so you can see that the more often you compound it, the more money you're going to get. Fantastic. Okay, next. Bacterial culture is growing according to the logistic growth function. Here it is. Fantastic. where y is the weight of the culture in grams and t is the time in hours. Find the weight of the culture after 0 hours, 1 hour, 10 hours, and then what is the limit as t approaches infinity. Great. So 0, 1, and 10, you're just plugging those values in. So let's do those real quick. So, oops, I guess I shouldn't hide my formula so I can copy it. So for part A, we get y. So for this one, we get t equals 0, t equals 1, t equals 10, and I'm just plugging those values in. So I get 1.25 over 1 plus 0.25 e to the negative 0.4 times 1. And so then for this one, I'm just going to get exactly 1 gram. Oh, because I'm plugging in 0. So times 0, sorry. So this all equals 1. Ugh, not all of it. E to the 0 equals 1. So then I get 1.25 over 1.25. And I get 1 gram. Part B. Now I plug in 1. Got those two confused for a second. Sorry. One plus 0.25 e to the negative 0.4. Okay, and so then this one I need to plug into my calculator, and I'm going to get approximately 1.071 grams. Next one, part C, we're plugging in 10, so I get y equals 1.25 over 1 plus 0.25 e to the negative 4. When I multiply that exponent, plug that into my handy-dandy calculator, I get 1.244 grams. Then the last question asks about the limit. Okay, so let's look at that. So I want to know what is the limit as t approaches infinity of 1.25 over 1 plus a quarter times e to the negative 0.4 t. Okay, so as t goes to infinity, this right here is an exponential decreasing function. So that piece right there is going to 0. Okay? And as that goes to 0, this whole chunk goes to 0. So then I am just going to get that this is the same thing as 1.25 over 1 plus 0, or 1.25 is my limit. Okay? And this notation of circling something and putting the arrow to 0 or putting the arrow to 1 or to infinity, that's actually proper notation to show limits. So you circle the piece that you can say, hey, as t goes to infinity, this piece right here is the piece with t, that's going to go to 0. So that's actually correct notation. So you're welcome to use that to show your work for limits. That's all I have today. Go ahead, work on the homework. Enjoy.